Okay, good morning. It's Brian here again with ECC, and today I want to talk about sensors that we use to measure rotation. So we use a couple of different kinds of sensors, whether this is for wheel speed sensors or whether it's for ABS sensors, as they're also called, or whether I'm talking camshaft or crankshaft sensors on my engines. We only have so many different kinds of sensors that I can measure rotation with. So one of the most common is a passive sensor, and that's my analog magnetic sensor, or also called a permanent magnet sensor. And these are great because they generate their own signal. I don't have to apply any voltage to them. Another sensor that we use is our Hall effect sensor, and that's the second one that I have right here. And they call this a radio impulse wheel sensor. If you notice, it has 3 wires. My permanent magnet only has 2 wires. With 3 wires, I need to have a power, a ground, and a signal return, and we'll take a look at those in a minute. And then I have 2 newer sensors here. So these newer sensors are also digital sensors, and they are Magneto resistive sensors, and I have 2 different ones. One is off a Chevy truck, and the other one is off of a Honda. And what makes these different is, even though they're the same type of sensor, is one of these, as you can see, has cutouts in the trigger wheel. The other one just is on the side, and it actually has an axial magnetic strip. So as the magnetic strip goes by, it changes the sensor signal. And these are built into the wheel bearing. So that's why it's critical on vehicles that use this last kind of sensor, that when we replace the wheel bearing, we put it in the correct direction. So we always verify by using a pocket screwdriver or something else magnetic which side of the bearing has the magnets on it. Because if I install it in backwards, I'm going to get an ABS light on, I'm going to have to take it back apart, and when I take it back apart, I just destroyed the $80 bearing I just put in. So my boss probably won't be real happy with me. So let's start. I'm going to start from left to right with you. I've got 2 channels up on the screen. Yellow is channel 1 right here. Green is channel 2. And I did something with these channels. I shifted my 0 voltages. So in this example, where this is 0 volts, and you can see the 0 in green on the other side, and where this is 0 volts, and you can see my 0 in yellow on the other side. So I'm using 2 different scales here. I'm using a 10 volt scale for my green, or my channel 2. So I'm currently at just under 5 volts with where I'm plugged in. And on my yellow scale, I'm using a much smaller scale. I'm using a 1 volt scale. Because I'm going to use that for my permanent magnet sensor, because it doesn't generate as much amperage or as much voltage. So, and it is directly related to how fast I'm going. So I can also change where these are on the screen. So I'm going to start off with by disconnecting channel 2 at the moment, and we can see we just dropped down. I've just got background noise. And I'm going to start rotating my vehicle. So I'm driving down the road. This happens to be out of a crank sensor out of a Hyundai, but the principle of the sensor is the same. The difference with having it on a crank sensor is I have this other little section where I'm actually missing a tooth, and we use that for synchronizing up where number 1 cylinder is. That doesn't mean that is where number 1 cylinder is. It just tells the computer where number 1 cylinder is. So this might be 50 degrees before top dead center. It might be 60 degrees before top dead center. It might be 20 degrees before top dead center. That's up to the engineers and up to the manufacturer. But this high part here is called a sync signal. And then I have my permanent magnet sensor signal, and we can see that's an analog signal. And what we notice about this signal is as I speed up, both my frequency, the amount of spacing between the lines, and my amplitude, the height, change. They both become greater. My amplitude becomes higher, my frequency becomes more, I'm cycling more times. If I go even faster, and we can see how the scope sees the pattern can actually change. Believe it or not, if I'm looking for a fault, I actually want to go slower. When I go fast, I get what? What's going on? All I see is a lot of noise. As I slow down, I can actually see more of the signal. Now I can also change the time settings on my scope. For example, right now I'm looking at 2 seconds of time. If I only look at 100 milliseconds of time, or 1/5 of this, I would see a lot more detail, but I wouldn't see patterns. If I looked at a lot more time, then I would just look at a lot of noise. I wouldn't be able to see detail. So anytime I set my time frame, it's a compromise. And I can always change that. Maybe I want to take, and I can also take recordings with this, where I can take a recording, go back and look at parts later. But for this lab, I chose the 2-second time frame. So I'm going to slow back down. I'm rotating, but I really don't have a lot of definition. So this is what I might see if I hook a scope up and I just rotate the wheel by hand. Because it's a permanent magnet sensor, it takes a certain amount of speed in order for it to generate a signal. And so that's one of the things we're looking at. As I increase speed, I get more of a signal. So one of the mistakes people make when they're testing these is they don't spin the wheel fast enough. And you can see, even though I'm going very slow for this motor, that'd be pretty fast if I was trying to spin the wheel around. So cranking speed on an engine is perfect. That's 800 RPM. I can get a good signal. Keep in mind, since my computers are digital, this is an analog signal. I have to have a certain amount of amplitude in the signal in order to switch the analog to digital converter inside of the computer. Because the computer is going to convert this into ones and zeros. So either I have a 1 or I have a 0. This has to move a certain amount in order for me to see that. So that's why if I use this for a crank sensor, my engine speed has to increase cranking up to 200 RPM, where I'm normally going to crank at. Hybrid vehicles, again, 800 RPM. Like I mentioned earlier, cranking speed at 800, that'd be a hybrid vehicle. So as I'm cranking up at 200 RPM, I now have enough amplitude for the computer to see it. If I'm cranking slow, I might not have enough amplitude. The computer might not fire the injectors, fire the ignition, start the car. On the case of a wheel speed sensor, if I slow down, I might not be able to have enough amplitude. You can see the only real height I have here is on that trigger part. I might not have enough amplitude for the computer to know that wheel's still going around, so it might apply the ABS brakes. So this is real simple. I have 2 wires. They call it a plus and a minus wire, but in reality, if I disconnect it, I can still get a signal out of it. Let's see here. But what I would need to do is I would need to hook both my wires across the sensor. So what I would do if I was going to test this on a car is I don't need to back probe it. I can just disconnect the connector, so then it would be unplugged, hook my power and ground on my scope up to the 2 wires coming out of the wheel, and I can get a pattern. And if you notice, if I swap these, I still get a pattern. So I don't even need to worry about which way I'm going. All I got to do is unplug 2 wires, hook the 2 wires of the lead up, look for a signal, spin the wheel, and I get a signal. And again, this is a crankshaft sensor out of a Hyundai. That's why it has the separator signal. So that's our first kind of sensor. That's a passive sensor. I'll plug it back in, and I'm going to leave my yellow lead connected. I'm going to put my black lead back to ground. So that brings us up to sensor number 2, my Hall effect sensor. So Hall effects are switches. In this case, my switch is going to go from power to ground, and I got this noise just from touching it. So apparently I have, well, electric personality, I think they call it. But you can see, so I'm generating a certain amount of electricity. Everyone does, and that's why shielding and things and leads are important. So I have 3 wires here. I have a power, a ground, a signal return. In this case, my power is 5 volts. So if I connect to that, I can see I got 5 volts. I also have a ground. If I connect there, I can see I have 0 volts. And I have a signal return. So all 3 wire sensors work this way. You have a power, a ground, a signal return. The power may be 5 volts, it may be 9 volts, it may be 12 volts, it may be system voltage. I have a ground and I have a signal return. And the signal return might be a digital signal or it could be an analog signal. In this case, it's going to be a digital signal. And I can see that because it goes from off, on, off, on, off, on. So here my amplitude will not change with speed. I can slow down, I've still got the same amplitude. If I speed up, my frequency increases, but my amplitude stays the same. So these have a big advantage. Being a Hall switch, no matter how slow my engine's going, I can tell the position of the engine. I can tell not only that it's turning, but by staggering different teeth inside the sensor, I can figure out, are we on cylinder 1, are we on cylinder 4, what's going on. So we use these a lot for camshaft sensors. because they allow us to have a great deal of accuracy. And I don't need a lot of rotation. The other advantage of the Hall compared to everything else we have here is I can use Halls and linear sensors. For example, a brake pedal position sensor. So my brake pedal position sensor is I push down on the brakes. Am I pushing it slowly or very quickly? A brake light switch just says, hey, the brakes are on, brakes are off. If I use a Hall, then did you slowly apply the brakes or did you jam them on really quick? Based on that information, the computer can now use the analog brakes and the anti-skid technology effectively based on the driver's request. What's the driver doing? We use this for clutch switches on cars that use a start-stop technology. So if my car is shut off at a stoplight and I start to let out the clutch, I want to start the car before the clutch is let out far enough to cause a vehicle to stall or to roll back. We use these on some power window systems to tell exactly where the window is in the window track. So we use Halls for a lot of stuff, not just things that rotate. Permanent magnets I can't do that with, and I can't do that with our Magneto resistive sensors either. That's unique to Halls. So Halls again are our 3-wire sensor. A lot of times Magneto resistance sensors are called a modified Hall because they're actually a digital sensor. One thing I want to show you is if I disconnect the lead, I no longer have a signal. I no longer have a signal because I have to apply 5 volts to the sensor. So once I reconnect the sensor, I get a signal back. That's going to be true of my next 2 sensors also, is that I would have to have power supplied to them. So a lot of books have me just test the resistance of these sensors. That doesn't tell me if the sensor is going to work. It tells me if the resistance of the sensor is correct. And I'll demonstrate on that on this next one. So now let me go to our radial impulse. And you can see this is also a square wave. It's happening much more quickly. And I'm only going from a 1/2 volt up to 1.5 volts. So even though we're applying more voltage to it, that's where we switch at. And if I want to see how much voltage is applied, I can check there. Look, I have 5 volts applied to it, but we're only switching between 1/2 volt and 1.5 volts. And if I speed up, again, my frequency increases, my amplitude stays the same, because this is a digital signal. And you can see that because no matter how slow it goes, it generates a signal. Now, if you notice, I have an air gap adjustment here. And on sensors that use an air gap adjustment, I have one for my permanent magnet also. As I adjust the air gap or change the air gap, it changes the electromagnetic field where the sensor might not read. So for example here, if there's dust or corrosion where the sensor mounts, or oil or dirt, and maybe that sensor when it's replaced isn't installed all the way, I might get a signal that looks like this. And you can see here, I'm no longer switching every time, I'm only switching part of the time. And you can see I've got some gaps. And I'm not going to see the gaps so much when I'm going fast. I'm much more likely to see them when I go slow. And so these gaps as I slow down on a wheel speed sensor, which is the only place we use this, are what cause a car to go into premature ABS lockup with no codes. Because all the computer thinks is that this sensor locked up when I'm slowing down, or in other words, that wheel locked up and stopped turning. So we're going to use the ABS brakes to try to free that wheel up. So this is very common customer complaint, where the customer says, hey, my brakes feel funny or they vibrate right when I come to a stop sometimes. Well, what it is, it's an ABS sensor dropping out. If I ohm out the sensor, it's obviously going to ohm out perfectly because there's nothing wrong with the sensor. The problem is the air gap. And that's why just ohming out a sensor is not sufficient for testing the system. We're always better testing things dynamically. Whether it's in the service bay and I hook the scope up, or whether it's driving down the road, I'm looking and seeing what's going on and have the scope hooked up. Obviously with wheel speed sensors, it's easier to do on the ground. So I can look at this. If I adjust the gap out a little more, look what happened. Less than a quarter turn, now I've got almost nothing, very intermittent. And now if I speed up, I'm still intermittent. All I did is change the gap just a little bit, quarter of a turn. If I gap out a little bit more, that was another 1/8 of a turn, if even that. the other 1/8 of a turn on flat line. So I haven't moved this very much. So you can see how sensitive this is if we're working on a vehicle and we're replacing a sensor on something where the hub is rusty. Or if we've had a lot of metal and rust get in and maybe all these little holes have started to get full of rust. So now there's not as much of a difference. It's much harder for the sensor to pick up. With the right air gap, I've got a good signal. So air gap problems are very, very common on these sensors. And I can do the same thing with my crankshaft sensor. If I back my crankshaft sensor up, you can see the difference in amplitude. I'm having the same speed. There where I'm very close, and here where I'm backed out. And if I get far enough away, it won't work at all. There's the adjustment on here won't let me go that far. But you can see how sensitive an air gap can be to a signal. So I could have something that there's nothing wrong with the sensor, there's nothing wrong with the trigger, it just might not be installed properly. Sometimes we use O-rings or other things where these installed and maybe someone took it out and the old O-ring's still in there, so it's pushing it out a little bit. So we get a lot of weird problems from rust and other things causing air gap issues. So if the air gap is adjustable, there's a specification for it. Most of these are not adjustable from the factory, so it's strictly a matter of making sure you have a clean surface and it's installed properly. And that's true whether I'm talking a cam sensor, a crank sensor, or a wheel speed sensor. So as we can see here also, I disconnected. No more signal because I didn't have any voltage going to it. So my last sensor here is the exact same kind of sensor, and we're going to see it looks exactly the same way. The difference is the magnets are on the side of the bearing surface instead of directly overhead. So here we normally don't have a gap adjustment issue because where it slides in is right next to it. I'm not coming in at 90 degrees to it, and it's going to work the same way. As I speed it up, I get more frequency. So the faster I go, the faster the increase, the amplitude stays the same. Now you hear me call this a square wave, and it really doesn't look like a square wave. And that's really a byproduct of the scope. So right now I set them at 2 seconds. So I'm going to come in and change the time on my scope and paint a different picture. Because all I'm doing with a scope is painting a picture. Remember, we're just looking at a signal over time. So I'm going to come in and change my time, and I'm going to go way in. So I'm actually going to come into, let's go down to 10 milliseconds. And at 10 milliseconds, I could speed up a little bit here. Boy, this doesn't look like much. This doesn't help me diagnose the car. But hold on, this is one of the powers of a digital scope. Is I can now save it, I can zoom it, and when many scopes, a Pico or an ATS, zoom in, the snap-on actually zooms out. So the snap-on, I need to take my picture very, very close to see the texture of a fence board, and then zoom out to see if I'm missing any. So here's what I zoomed out to. And now what do I have? I just have a whole bunch of noise. I can turn this off, which is really nice if I'm working on a vehicle. I can shut it off. I don't have to listen to it. If it's hot, I don't have the hot car running the shop. And this doesn't really look like anything. But wherever I put this white line, the dashed white line in the middle, I can zoom in. So if I zoom in to times 64, it looks like this. So this is great for comparing where things happen among different patterns. If I want to look at the detail of this pattern, I'd want to zoom in even more. So there's times 16. Now does this look like a square wave? So the fact it didn't look like a square wave before when I was looking at 2 seconds is because of how far out and because of the limits of the scope. So this particular scope does not give good detail if I'm looking at a signal over a lot of time. In order to get the detail and really test the integrity of the signal, I need to take a recording that I can look at. If I just want to see if it works, being live works just fine. But if I want to look at detail and our integrity, now I want to be able to take a capture very, very close, look at everything, and then I can see what's going on. And so we say you look close for detail, you look back for patterns. And to illustrate that, let's put a fault back in our box. Okay, so now let's take a look at how focusing in might allow us to miss something or I want to focus out to see it. So I'm going to go back over to this sensor that I can adjust the gap in. And I'm going to start it up. And I'm going to slowly bring the gap in. And I can see I've got a signal. And the question is, do I have a signal all the time? I can't tell here. But if I freeze it and zoom it, now I can get a better idea of my signal. I can see here that I did have a signal all the time. So that's how I would use this tool, and this is based on what I'm looking at. Now I can also go through different parts of the movie, and here's where we stop going around. So here's where we stop. So you can see by being able to compare two sensors at the same time, I can see these both stopped at exactly the same time. If I was looking at wheel speed sensors or a cam and crank sensor on a car that's stalling, and one sensor stops before the other, and I know the engine was going around or the car was going, that instantly tells me which sensor is going bad. So that's where we want to compare a couple of different sensors. And so that's why we use two channels, is because I can use one to compare it to the other. And so I would actually test a sensor I know is good, at the same time I'm testing a sensor that I think might not be good. We can see here where this sensor is not working sometimes, but this sensor always is, which means if they're both measuring the same thing, such as an engine, or we're measuring a vehicle going down the road, we can see that, hey, I got one, not the other. So let me go over where I have two sensors that look the same. I'll reset the scope. Okay, so what I just did here is I took a capture of our two Magneto resistive sensors. And I have one sensor here and one sensor here. And we can see they don't look the same. So if these is two wheel speed sensors on the same vehicle, this would be a big problem. So they should all look the same. So the question is, which one's bad? Well, I want to zoom in a little bit to see that. So let me zoom in here a little bit. And now I can see what? I have a square wave here, but I'm what? Missing teeth here. Since these are both for wheel speed sensors, and the car's going down the road with the wheel speed sensors here, and this one always has a pattern, and this one doesn't always have a pattern, tells me instantly that's the sensor with my problem. So again, if I'm diagnosing a car that goes into an ABS lockup condition just before a stop, I have no codes. I don't know which sensor is causing the problem. I got 4 to choose from. So I can do a couple of different ways. I can cheat and use a scan tool and look for which sensor drops out. The problem is if I have permanent magnet sensors, they don't work below 3 miles an hour, and that's normally when the problem happens. So it's real hard for the scan tool to show. Sometimes some scan tools will, if you've driven the car and gone over 20 miles an hour, it no longer lets you see the data until you reset the scan tool. So that's really frustrating because they don't want you looking at the scan tool while you're doing 70. So they build it into the software to be safe. So that's an issue we have. So sometimes we're kind of playing, shooting blind, trying to figure out which sensor is bad. So that's where we might use a scope on a couple different channels, drive it, and see what's going on. And I can zoom in a little bit more, and you can see where, if I move my line over, and I can see where I dropped out. You can really see the difference here. And you can see I got a nice square wave here. I don't have a nice square wave here. Both wheels were going around. This is the wheel with my problem. That's what's causing my customer complaint. So a lot of it is about analyzing the data, hooking it up. What kind of sensor am I working on? Based on the sensor, what kind of pattern am I going to get? As you can see with these sensors, as we proved, if they're disconnected, no signal. So if I think I'm testing one of these, but I'm actually testing one of these, and I just disconnected and put the scope up and go, gee, there's no signal, I need a new sensor. Guess what? The new sensor is not going to have a signal either because it's the wrong kind of sensor. So I can do a couple of different things. I can go into Mitchell or All Data and look up the information to find out what kind of sensor it is, or what? I can disconnect the connector and see if I have voltage coming to it. If I have 5 volts going to it, guess what? It's a Magneto resistive sensor. If I don't have any voltage going to it, then guess what? It's a permanent magnet. When we know how things work, we can figure out how to test it. So hopefully I was able to give you some good information today on the types of sensors we use for measuring rotating devices. We talked about our permanent magnet, we talked about our Hall effect, and we talked about 2 types of magneto resistive sensors. The difference between them, we talked about air gap, how air gap can affect our signal. We talked about advantages and disadvantages of a Hall that will work at any speed versus a permanent magnet that has to have a certain amount of rotation for the computer to see something's happening. And we also talked about the 2 different types of sensors where an air gap is going to really affect it if I'm using a permanent magnet or a magneto resistive, where if I have too much air gap, as we can see, it can damage the signal integrity. which again is a problem, but replacing the sensor isn't necessarily going to fix that. And we also talked about the axial style where the pickup is actually in the bearing, and if you put the bearing in incorrectly, there's not going to be a place for the sensor to pick up the signal, and it will not work properly. So it's important to understand what kind of sensor we're working on, then we know how to test it. So thank you for joining me today.